Bismillah ar-Rahman ar-Rahim. Today we are going to start a new unit about the analysis and design of synchronous sequential circuits. Okay, so we will start by an introduction, and then we'll discuss latches and flip-flops, and then we'll talk about the analysis and design of sequential circuits or clocked sequential circuits. Okay, and sometimes clocked sequential circuits are also called synchronous sequential circuits. Okay, so either synchronous or clocked, they are both mean the same. Okay, so synchronous sequential circuits and clocked sequential circuits are the same thing. Let's start by an introduction. So sequential circuits are a superset of combinational circuits. So they are combinational circuits with additional components. Okay, what is this additional component? Which it is the memory component. Okay, the memory is supposed to keep track or keep record of the state of the circuit. Okay, state of the circuit. So we have a combinational circuit, all right, that has k external inputs. Okay, and it produces an output. Okay, and it produces also the next state to the memory, so that it computes the present, which actually having the output, its output as the present state. Okay, so this next state will affect the memory element to produce another new present state. Okay, so the input of the combinational circuit here is both the present state of the memory elements as well as the external inputs. Okay, and it has the output of external output that is used by some other circuit. Okay, and it has also the output that is associated or that is sent to the memory. Okay, so the memory, the main purpose of the memory is to track the state of the circuit, and the circuit has both present state and the next state. Okay, and to simplify the concept of state to you, okay, imagine a program. Okay, let's say that we have a program here. Okay, let's say that we have, for example, let's say while so we have I, okay, while I is less than 10, and then we have, like, for example, s equals 0, okay, so s, and finished. So what does this program do? Who can tell me what is the output of this program? It's S. The output is S. But what does it do? What does it compute?
Does it multiply I by S?
This is multiplication. Is this a multiplication sign?
The sum of the numbers from 1 to 10.
It sums up the
S and I.
Yeah, but it sums up the numbers from
1 to 10.
1 to 10, including 10.
No, just exclude.
Yeah. So, but there is a mistake that we have done. What is the mistake? Anyone? We
initialized I as 0.
Okay, fine. That's fine. Zero plus anything is the same thing. But will this loop ever get out?
No, it's an infinite.
Yeah, it's an infinite loop. So I need to what? Increment my I. Yeah. So again, let's revise our output. The output is the sum of the numbers from 1 to what?
9.
9. Excellent. Yeah, it's not to 10. Okay, it's not to 10. But let me ask you this now. Let's say that you are like you are some quantum object, okay, that you are monitoring the execution of this code from the one angle or another, okay, and you are like monitoring the memory here, okay, as the program executing. So I, for example, is now 5, and then S is something, okay, and that's it. Do we need any other information to describe the number? I mean the program progress. Do we need any other information? So if I tell you what is S and what is I, you should know exactly where the program is, right? Isn't it?
Yes.
Yeah. So this is in a sense, this is called the state of the program. Okay, the state of the program. So the state basically is the variables, the various variables in the program taken at different run time. Okay, different run time. So in our case, we have some variables that are composed of bits. Okay, these are bits. All right. So we can store some bits to indicate the state of our synchronous sequential circuit or sequential circuit in general. Okay. So the variables in a program, in a high-level program, represent the state of the program during runtime. Okay, the values of the variables represent the state. So this is called the present state. Okay, and then this will lead to, you know, that by the execution, you know, the control of the program. By the execution, you know that this will lead to a next state. Yeah, a next state. All right. The next state will contain I equal what? 6, and then S will be equal to something, which is the sum of the numbers from 1 to 6. Okay. So this is the next state. Okay. So you can see that here. So we are computing the next state that will be stored in the memory, and the present state is already stored in the memory. Okay. So the next state will overwrite the current present state. Okay. So this is a general model. Okay. Then later we will discuss the details. Okay. So now sequential circuits can be categorized into 2 categories: either synchronous, and also known as clocked, as we said at the beginning. Okay, synchronous or clocked. And they can also be asynchronous, which is the A here is for the opposite here. Okay, A here it means not synchronous. Okay, not synchronous. So synchronous sequential circuits, in synchronous sequential circuits, the state of the circuit, which is the bits that are in the memory. Okay, the state of the circuit changes, or the changes in the state of the circuit are synchronized with what we call a global clock signal. Okay, we have a global clock signal, and the state changes according to this global clock signal. Okay, so to indicate that, we have a global clock signal that is connected to the memory elements here. This is the exact same model, but we added the clock signal here. Okay, so this is to indicate a clocked sequential circuit. Okay. So the changes here, the changes of, what do we mean by changes, by the way? What do we mean by changes? We mean the changes in the bits. Bits can be zeros and can be ones, right? So the change can be from 0 to 1 or from 1 to 0. So these changes can be synced or can be synchronized with the clock, what we call rising edge or falling edge. And let's see what we mean by that. Now, this is the, let's just erase this. Okay, this is what we call the clock signal. The clock signal is a continuous train of pulses. Continuous train of pulses and it is a periodic signal. Okay, so this is the clock cycle. It's called the clock cycle or the clock period. Okay, it's from here to here. Okay, and this is denoted by P, for example. Okay, if this is P in nanoseconds, for example, or picoseconds or something like that, then what is the frequency of the clock? It's 1 over P, right? 1 over P. Yeah, the reciprocal of the period is the frequency of the signal. So what does the frequency mean? It means how many cycles per second does the clock have? How many cycles per second? So how many periods per second does the clock have? This is the definition of the frequency. And the period is how long does it take for one cycle? How much time does it take for one cycle? So this is called the period and frequency of the clock. Now, there are other definitions about the clock. We call this level here, this level, we call it the positive pulse of the clock. And this one, we call it the negative pulse of the clock. Or this is 1 and this is 0, okay? Another definition, okay, that is relevant to the clock is what we call the rising edge or the falling edge. All right, so where are the rising edges other than these? Okay, we have this rising edge, this rising edge, this rising edge, this and this, okay? Where are the falling edges? This is a falling edge, falling edge, falling edge, falling edge, okay? Rising edge is also called a positive edge, okay? Positive edge means going from 0 to 1, okay? Going from 0 to 1. The transition from 0 to 1 is called either a positive edge or a rising edge. And going from 1 to 0 is called a negative edge or a positive or a falling edge. Negative falling or positive rising, okay? All right. Any questions so far? So we have here, what we have is what I just said here is that the changes of the present state, okay, can be synchronized with the clock rising or falling edge, okay? So what does this mean? For example, if the changes are synchronized with the rising edge, then I expect changes only during the rising edge of the clock. Only during the rising edge of the clock. All right. So the change can happen, the single change can happen only during this very tiny period of time. Okay. If the input, for example, changes during outside this time, then the changes are not captured by the memory elements, okay? For example, suppose that my input changes, okay? My input changes here, okay? My input, this input here, okay? My input signal changes here and then, which produces a change in the next state, okay? And it changes here, exactly. All right, and this change will have no effect whatsoever on the memory elements if they are positive edge, synchronized with the positive edge, okay? It will only have an effect when it lasts, the change lasts, okay, until the next positive edge, okay? Then it will have a change, an impact, okay? So this is what we mean by synchronizing with the clock rising or falling edge. All right. Okay. We will see how to do that, by the way. We will see gradually how to do that. Okay. We will study the positive edge triggered and negative edge triggered flip-flops and their structures. Okay. All right. Now, we said something about synchronous sequential circuits. What about this thing here, which is asynchronous sequential circuits? Asynchronous sequential circuit, it means that the state can change at any point in time, okay? and this makes the circuit very difficult to analyze and very difficult to design as well. So in this course, we only study synchronous or clocked sequential circuits. Okay, we do not study asynchronous sequential circuits. So now we turn our attention to the memory part. Okay, what's inside this memory part here? Okay, this memory part. All right, this memory part. What is inside here? Okay, we need to know what is inside. So the memory can be one of two kinds. Okay, the first kind is latches. Okay, and the second kind is flip-flops. Okay, each one of these, okay, can store one latch or one flip-flop. One latch can store 1 bit of memory, just 1 bit, and one flip-flop can store 1 bit of memory. Okay, so if you need, for example, 5 bit of memory to store your state, then you will have to use 5 latches or flip-flops. Later we'll see that latches are not really good for use with clocked sequential circuits, but they are used to implement flip-flops. That's why we study them. Okay, otherwise latches are part of asynchronous sequential circuits. Okay, we study them only to construct flip-flops. Okay, and then we'll be using flip-flops when we start using, after studying the latches, we'll only use flip-flops. Okay, all right, so let's start with the simplest latch, okay, which is the SR latch. Okay, the SR latch. But instead of starting with this this structure here, I will show you where it comes from. Okay, so there is what we call a feedback. But before I show you where it comes from, I want to discuss the functionality first. Okay, so we have what we call a reset input, which is R here, and Q. All right, so my bit is Q. My bit that I want to store is in Q. This output here is my bit. All right, and it can be a 0 or a 1. All right, this bit here is just for repeated. Okay, it's the complement of Q, so it doesn't add information. It's not an extra bit. No, it's just the complement of this bit. Okay, and it comes for free. Okay, because of the design of the latch. So we have a reset input and a set input. From the name, you can understand that reset resets Q to 0, and set sets Q to 0. But there are constraints. Okay, you cannot use them just like that. Okay. Now, when you want to reset, okay, you set you assert R1, okay, and drive S to 0. You have to drive S to 0. So a reset operation means SR is a 0, 1. SR is a 0, 1. So if SR is equals a 0, 1, okay, then S is 0. Okay, so S is not active, and R is 1. You see that? If this is the case, then Q will be equal to 1. All right, Q will store 1 in Q. All right. In case S and R are 1, 0, on the other hand, so my S is 1 and my R is 0. So my R is not active in this case. Then what happens? What happens is that my Q will be, I'm really sorry. I just messed up here. So let me do that again. So if S and R are 0, 1, then this is a reset operation. Okay, so the Q will become a 0 here. Okay, after executing this command, after applying S and R to be 0 and 1, I get a 0 on Q. When I apply SR to be equal to 1, 0, okay, then my S is 1 and my R is 0, then I expect S to be Q to be 1, okay, to be set. All right, and when Q is 1, Q complement is going to be 0. Now the magic happens when both are 0. When S and R are both zeros, then what happens? There is no change.
Depends
Yeah, well, depends on what?
on the last. What was it last time?
Yeah, so it doesn't change. The value doesn't change, because in this case, the 0 is the non-controlling value of the OR. So whatever the other input has, okay, it will dictate the value of the output. Okay, so if this is a 0 and this is a 0, then this is a Q complement. Okay, then the output here will be Q. Okay, because 0 NORed with Q complement is Q, right? 0 NORed with Q complement is what? It's 1 ANDed with, by De Morgan's law, Q, right? Which is Q. Yeah? So Q will not change. And similarly, Q complement will not change. Okay? It's because it becomes 0 NORed with what? With Q, which becomes Q complement. Yeah? Okay. Now, this is the operation as explained from a high level. Okay, so this is the operation here. So S and R, and then this is Q. So if S and R are 0, 1, this is a reset. Okay, Q will become a 0. If S and R are 1, 0, then this is a set. If they are 0, 0, then this is a no change. Whatever the value that Q has, it will remain at this value until you give it another command. 1 and 1, on the other hand, now if you think about this input pattern, you're saying, as if you are saying, sit and reset at the same time. Can you do that? Answer is no. Okay, you cannot do the sitting and resetting at the same time. Okay, so it results in a conflict. Okay, it results in a conflict, and it will produce what 0, 0 in the Q and Q complement. Yeah, because if this is, let's say, if this is a 1, if this is a 1, and this is a 1, okay, then what happens? Okay, what happens is that no matter what this input is, the output here is going to be a 0. And no matter what this input is, the output here is going to be a 0. So you're saying that Q is 0 and Q complement is 0. Is this possible? No. Answer is no. It's a contradiction. Okay. For this reason, this is not allowed. This is a forbidden input combination. And yet the situation becomes worse if both transfer to 0, 0 after that. Okay, if this is the case, then we will have a continuous transition between 0 and 1 in the queue. Okay, so no longer the 0, 0 will become a no change, but it will become an unstable state. Okay, unstable state.
Like a clock, doctor?
Yeah, it will become alternating between 0 and 1. Yes. But avoid this by all means. Okay, avoid this by all means. This input combination. Okay. So let's go back and see where this is coming from. Okay, where this is coming from. Okay, so let me start with a simple inverter. Okay, and let me say that the input is X here. What is the output of the circuit?
X.
X.
X. So it doesn't harm if I connect both input and output to each other, right? Because they are at the same potential, right? Same level. Okay, the they are both, I mean, if they're not connected, they are not connected, okay? This net here is virtually the same net as this one, okay? So it doesn't harm if I connect them together, okay? But what happens if you do that? If you do that, then if X, for example, is 1, what happens? This is going to be a 0, right? 0. And this is a 1. So this is going to reinforce itself indefinitely. So this one here is stored forever. Or this 0 here is stored forever. Let's call this my Q. And this is Q complement, okay? Yeah? So this is how you store one bit using back-to-back inverters, okay? Now, to make this interesting, the only thing is that this thing here doesn't allow us to control it. And it's very difficult to change or to set or reset the inverter. Who can tell me, from what you learned so far, okay, who can tell me how to fix this problem or how to improve this circuit?
Doctor, we
Yes.
can just apply a voltage to the right side.
A voltage. So
I mean, like, just
On the
set
right
another
side?
variable and set it to 1.
So you want to say, well, this is like yeah, it's like X here, okay? So you
And Y to the right.
And Y to the right?
Yes.
Okay, that could be good. Okay, that's how what we call SRAM is created. Okay, but we're not into that. Okay, what we want to do is then to come up with the SR latch. Okay, now the way to do it is to convert these inverters to NOR. Okay, convert these inverters to NOR, right? And we know how to do that, right? We know how to do that. So the only thing that you need to do is right. Yeah, and I can, for example, NOR it with a 0. Okay. Yeah. And it's still the same circuit, right? Exactly the same circuit, except that I'm NORing it with zeros so that I keep the value not changing, right? So where is my Q and my Q complement? This is my Q, and this is my U complement, right? But now I can apply some other inputs to this and this, not only 0, 0, right? So 0, 0 means no change here, right? 0, 0 means no change here. But what if I apply a 1 here? Let me use a different color. If I apply a 1 here, what happens? What is going to happen here is that this is going to be, before the bubble, it's going to be a 0, all right? And after the bubble, it's going to be a 1, right?
Isn't it the opposite, Doctor?
I'm sorry, yes, you're right. 1, and then a 0. Yeah?
Yes.
Okay. So this must be the reset input. Yeah? Because I managed to reset Q to 0, although I don't know the previous value of Q. Okay? Now this 0 comes here. Okay? And I have a 0 here. So 0 ORed with 0 is 0. And then inverted, it becomes a 1. Right? Yeah? So 1 ORed with 1 is also 1. But inverted, it is 0. So this is the stable value of the Q and Q complement. It is 0 and 1. Okay. So this we managed to reset the Q to 0. And remember, if this goes back to 0, then we maintain the value of Q. Okay. Of course, assuming that this is 0 as well. The sit is 0. So this is sit. Okay. And if sit becomes a 1 now, after being reset is driven back to 0, then what happens? This is going to be a 1 ORed with a 0, which is a 1, and then after the bubble it becomes a 0. Yeah. And then 0 ORed with 0 is 0. Okay, after the bubble it's 1. Yeah. So this is my sit input, definitely. Okay. And then if I pull the or drive this back to 0, then it is again no change. So this bit is going to remain forever. Do you see that? Any question about this?
Doctor, isn't this the same as the previous
Yes,
example?
but I just showed you where it comes from.
Okay.
Yeah. So if you just twist this OR gate and then make its input to the pointing to the right, just like the top one, you wind up with this structure here. Okay. I just showed you where this is coming from. Okay. So it all starts with inverters back to back. Okay. And then you change the inverters to NOR gates. Okay. To get what we call the SR latch. Now, if you change the inverters to NAND gates instead, you get what we call the second type of latch, which is S complement R complement latch. Okay, with NAND gates. I'm not going to show you how this is where this comes from. Okay, you know how to do that yourself, but only I'm discussing the function table, of the S complement, what we call S complement R complement latch. Please guys, wake up and notice that I'm discussing a new type of latch now. Okay, it's a different than the SR latch that we discussed. The SR latch uses what? NOR gates, and this is S complement R complement latch uses NAND gates. Okay. All right, now why is it called S complement R complement? Because these signals are now active low. Okay, active low. So the signals are active when they are low. Okay, in comparison to the previous one, the SR latch. In the case of SR latch, the signals were active when the signal is high. Okay, so when it is 1, but here when S complement is 0. It is going to be active. When R complement is 0, it is going to be active. Okay, so here you see S complement is 0 and R complement is 1. So this we expect this to be a set operation. So this is Q is set. 1 1 on the other hand is permitted here. Okay, because it corresponds to no change in here. Okay, no change. All right. But 0 0 is not permitted. It's prohibited and it's undefined, and it leads to instability. Okay. 1 0 or S complement R complement drives Q to 0. Okay, and 1 1 is a no change. Okay. Any question? So this is the second type of latches. Okay, that we studied today. I'm going to move on to the third type of latches. Okay, if you don't have a question, please let me know if you have a question. Otherwise, I'm going to move on to the next type of latch.
Yes, doctor.
Yes.
A NAND gate. Why did we complement S and R?
This is a notation. Yeah, this is a notation. It's just a notation. So it means that this is S complement. It means that it is the signal is active when it is 0. Okay. When it is 0. So when S complement is 0, which means when S is 1, basically. Okay. When S complement is 0, then I have, of course, an R complement is 1. When S complement is 0 and R complement is 1, I have a set operation. Okay, and when S complement is 1, so it's not active here, and R complement is 0, which is active, then we have a reset operation. And when both are inactive, meaning that they are both ones here, okay, it means that there is a no change. So this is why we are complementing them. This is like a common thing that we use, okay, a common nomenclature. Okay, it's to indicate that the signal is active low or active high, to indicate the value of the signal that is active. Okay, so when I tell you that the signal, I have a signal that is enable, for example, complement. All right, I'm calling the signal enable complement. Then you should know exactly. You should know directly that this signal is active low. So it is active when it is low. So it is when enable complement is 0, then this is the active value. So I'm activating, for example, this component when my enable complement is 0. However, if I give you enable without a complement, then this is an active high signal. This is why it's called, we have the bars on top of S complement and R complement. You get that? Yeah.
Yes, thank you.
Okay. All right, so let's move on to SR latch now with clock input. Okay, with clock input. Okay, so now notice that this one here. Let me ask you this. Let me just draw a box around this. What is this inside the box here? What type of latch is this?
It's our NAND.
Yeah, it is an S complement, R complement latch, right? And we are preceding it by these two NAND gates, okay? These two NAND gates, all right? Now, if C is 0, let's say that C is 0 here. So I have a 0 here and a 0 here, right? Now, if you have a 0 at one input of the NAND gate, then the output of the NAND gate will be what?
Always 1.
Always 1. Excellent. So here it's 1, and here it is 1. And we said for the S complement, R complement, 1, 1 means what?
No change.
No change. Excellent. So when I have my C 0, and so I don't care about S and R, this is a no change. Okay. The other possibility is when C is 1. When C is 1, okay, what is the output here at this AND gate? It's 1, 1, NANDed with S, right? Which is S complement, yeah? This, right? Isn't it?
Yes.
And this one here, the output of the NAND gate is 1 ANDed with R complement, which is R complement. This is nothing but, okay, it acts like an S complement, R complement latch, okay, if C is 1, or actually it acts like an SR latch, okay, because we are giving S and R now, not S complement and R complement, okay. So S and R are active high signals, okay, active high signals, okay. So when S is 1, it is active, and when R is 1, it's active. So here we have 0, 1 for S and R. This is a reset, and 1, 0. This is a set. Okay, and 0, 0. This is a no change. You get that? It is important that you understand, guys. Okay. All right. Now we move on to the next type of of latches, okay, which is the D latch, okay, with a clock input, okay. So we are sick and tired of this undefined state here. We don't want it, okay. We don't want it. So what happens is that you notice that S is always the complement of R when we want to set or reset, right? You see that? So why not have a single input? Okay, call it D, for example. When D is 0, we reset, and when D is 1, we set. So we compute S and R using D, okay? So my D is going to be S, okay, and my D complement is going to be R. So eventually you have here D, and here you have D complement. So no way, in no way, you will have 1, 1 for S and R. Okay, do you see that? There is no way that you can get the undefined operation for the D latch. Okay, so again, you have this structure here. Where is it? Let me just use this. This structure here is the SR latch with clock input. Okay, you see that? And then we controlled the S and R to get D and D complement instead. Okay, so we got rid of the undefined input combination. Okay, so the function table now is that when you have C is 0, this is a no change, and when you have C is 1, this is nothing but copying D to Q. Okay, so Q is equal to whatever the value of D is. Okay, if D is 0, Q will be 0. If D is 1, Q will be 1. This is a very attractive D latch. Okay, so, and these are the graphic symbols for the latches. This is an SR latch. It has 3 inputs, S, C, and R. Okay, notice the bubble here, okay, which is preceding the Q complement here. And we have S complement, R complement, and there are bubbles here, okay. And this is C, okay, and then we have an S complement, R complement latch, okay. And there is a bubble here to indicate that this is Q complement, okay, in addition to Q, of course, in both cases. And this is the D latch, okay. It has D and C, and it has Q output and a Q complement output. It's the simplest and most useful latch among all of them. Okay. All right. Now, what are the problems with latches? Latches, especially the one with clocks, okay, they are level sensitive. They are level sensitive. Okay. Let me examine this circuit here for you. And let me ask you that we provide a clock signal here like this. Okay, and X, my X, okay, as an external input here is equal to 1. And my X is XORed with the previous value, the current value of Q. Okay, so the output here is either, so this is my D here. The output is either what? It's not either, actually. It's going to be Q complement, yeah? It's going to be Q complement because Q XORed with 1 is equal to Q complement. This is by XOR properties, right? So each time, okay, the clock is high, I will keep complementing Q. Do you see that? I want you to see that, guys. Do you see that? Each time the clock is high, like this, the clock is high here, from here all the way to here. I will keep complementing Q. Do you see that?
Yes, this is
okay. So whoever said yes, I'm going to ask you a follow-up question. What is the final value of Q after the clock goes down here? شباب.
Is it random, doctor? Based on the how long
Yeah,
the clock was up?
it depends on several parameters. Okay, the length of the clock period, and also the propagation delays and stuff like that. It's so many parameters. So we are so uncertain what is the value of Q. Okay, we don't actually know. Okay, we have no idea what is the final value of Q. For this reason, for this uncertainty in the values of latches, we do not use them for synchronous sequential circuits, but we use flip-flops instead. Okay, and we will start flip-flops inshallah from the next class, which is going to be tonight. Okay, tonight I'm going to start to discuss the flip-flops, so make sure that you watch the video for tonight. Okay, all right. If you want to attend, let me know, and I will be glad to give you a message before beginning the lecture by 10 minutes. Okay, all right. Let me stop recording.